Hi, in this video we will learn about vectors in M space and what is Euclidean M space or M. Well, let me start with the first thing is that all vectors, so this is the first thing, all vectors with M components. Remember, so far we have been dealing with vectors with two components or three components. In general, we can have vectors which has any number of components you like. All vectors with M components form the space we denote it by R to the power M, which is M-dimensional Euclidean space. Well, it means technically it has meaning behind that, but at the moment you need to know that these are vectors with M components, and well, we will learn what are the operations. Just one quick remark here is that we have worked with R2 and R3, meaning that M is either 2 or 3. Well, now we want to do it for general M spaces, 4, 5, and any number of components you like. Let us start with vector operations here. First thing, the scalar multiplication still exists. Scalar multiplication. Again, you pick a C scalar. Let C be a scalar. Then C times U from M space, M Euclidean space is C times first component, C times the second component, and C times the mth component. Just multiply the scalar to all the given components. Well, then the next thing is vector addition. Vector addition. It means that if two vectors are let U and V be vectors from M space, then U plus V is a new vector with M components whose components are given by sums of corresponding components, U1 plus V1, U2 plus V2, and UM plus VM. And then, while in the similar way, we can have vector subtraction or differences, which is given by U minus V is you do U1 minus V1, U2 minus V2, and UM minus VM. Something that you need to note here is note 1 is that similar to the 2 and 3 dimensional, similar to R2 and R3, the above operations in m spaces are done, remember the keyword, component wise. So you do the operation, scalar multiplication to all the components. Add the corresponding components. Subtract the components, the corresponding components. And note too is that while doing these operations, we are allowed to use only vectors which have the same number of components. So while performing vector operations, we are allowed to use vectors with the same number of components. We cannot add a vector with 3 components to a vector with 4 components. We cannot deal with those kind of situations. Okay, so it's very similar. It's most like a review of what we learned in section 1.1. But then how about the products we had? Remember that we had dot product and cross product. Cross product is only for 3-dimensional, R3. But dot product works for all M spaces. So if you have 2 vectors, U and V from M space, you find the dot product. Very similar as before. You multiply the corresponding components. How many of them you have doesn't matter. You multiply corresponding, then add them. That number is U dot V, or the cross product of these 2 vectors. And then the length of a vector in Rm. Well, if we have a vector in Rm, U, again the length is shown by this notation, and it is in practice square root of U dot U, which means that you square each component and then add all these numbers and then find square root of that. Again, square each component and then add them and find the square root. Well, remember that similarly a vector of length O1 is called a unit vector, and every non-zero for every non-zero vector U, there exists first a unit vector with the same direction. This vector, you remember, we found it by, you have U vector multiplied by 1 over length of U, and there is also another unit vector with the opposite direction, which is again very similar. Multiply u by 1 over length of u, but to get opposite direction you multiply it by negative 1. So that is very similar to the 2 or 3 dimensional case. But if you remember, we had more things. For example, we had distance of 2 vectors. Again, we denote it by d of u and v, and it is basically length of u minus v. In other words, you first subtract the corresponding components, square each one, add them, and then find the square root of this. That's again very similar to what we had before. After dot product, remember there was this cosine formula. Cosine formula still works here. So if theta is the angle between u and v in Rm, then we can find the cosine of the angle. Cosine of theta is u dot v. These are m vectors, so you do apply this definition for the dot product, and then divided by the length of u. For that, again, you use this formula, and then divided by length of v. This is exactly same formula, but the operations or the computations you do is for vectors with 3 components. And one more thing that we had before was the orthogonality test. Orthogonality test still works here. So 2 vectors in Rm are orthogonal if and only if their dot product is 0. In other words, u is perpendicular to v if and only if u dot v is equal to number 0. As you see, everything is similar to what we had in 2 and 3 dimensional, but with one difference, that instead of working with 2 or 3 components, we are now working with m components. Scalar multiplication, vector addition, vector subtraction is component 1. Dot product is multiply the corresponding components, then add them. Length is similarly can be found. Distance and cosine formula and orthogonality test still hold.